All right, so this is test B for the extra credit. And please make sure that you're writing things in a nice, orderly, neat manner. I'm having to use several slips of paper to get it under the document camera, but yours should be very orderly and neat so that we can grade it well so that you can receive all the points. So a new vaccine is being readied to fight the COVID-19 virus. The new vaccine is believed to be effective in preventing 87% of the population who have not contracted the virus from contracting the virus. I'm just going to circle that. Um, of those who have contracted the virus, it's believed that the vaccine will be effective in preventing 95% of them from contracting the virus a second time. The vaccine is believed to be more effective in those who have already had the virus due to the antibodies that were built up in the body as the body fought off the virus. New York City was at one time the epicenter for the COVID-19 virus in the United States, and it's believed that 22% of the population of New York City has contracted the virus. So basically, we know we have three numbers. We have a lot of information. We need a way to organize this. I'm not even sure at this point when I read this thing, it's like, gosh, where are my two variables? There is just a ton of information. There's so much information, and because I have three numbers, I'm going to sit there and see if I can't make a table out of this just to organize things, whether or not I need the table or not. It'll be worth it just to organize my information. So when I'm making a table, one of the key things is there one number that's associated with only a single variable? So the new vaccine is believed to be effective in preventing 87% of the population who have not contracted the virus from contracting the virus. Ooh, we have two things here. Those who have not and now contracting it contracting it. So this looks like this is two variables, right? Because they haven't contracted it and they won't contract it. It's 87%, but it's of that group. And that word "of" is generally a key word for indicating that it's related to two variables. Then I go to this next one. Of those, so of lets me know that I'm probably going to be working with two variables. Of those who have contracted the virus, in other words, we're looking at contracted the virus, it's believed the vaccine will be effective in preventing them from contracting it the second time. So of this one is also two variables. So hopefully this is my one with singular variable. So New York City was at one time the epicenter for COVID-19 virus in the United States, and it's believed 22% of the population of New York City contracted the virus. So here's what we know about this. We know that they contracted the virus, and it doesn't talk about a vaccine. So it's like, oh, okay, these people have contracted the virus. This looks like this is my singular variable, so it's like one. So I'm going to start with that being where I'm going to start with making a table, and then we'll start labeling and try and figure out what our variables are. So when I go to this, and by the way, once again, I don't always know exactly where I'm going with things, but I do know that if I isolate it down to one variable, I have a good starting point, and just the table helps me organize things a lot of the time. So this is 1.0. All right, so 22% of the population contracted the virus. So this means 0.22 and 0.78. Now we have virus and vaccine, and I noticed that, and both of those have a start with a V. So I'm going to go ahead and change, instead of virus, I'm going to use D for disease. So 22% of the population caught the disease. These did not catch the disease. And once I have that value, I can just bring it straight up. I really don't even have to think about it. And remember, small mistakes early on, you can go ahead and just scratch them out and start over if you need to. All right. Now, the new vaccine is believed to be effective in preventing 87% from contracting the virus. Oh, well, wait a second. So this is disease, and we could say vaccine, and then they get the disease, and vaccine, and they don't get the disease, vaccine and no disease. So And you could put them in any order. It didn't matter which place you put them. Just make sure your numbers follow it. So the vaccine is believed to be effective in 87% of the population who have not contracted. So no disease, not contracted, that's right here. All right, because this is vaccine and you don't get the disease, 87% chance if you haven't already had the disease. So this means this is 0.13. All right, I'm going to go ahead and multiply those out. When I multiply those out, I end up getting 0.1014. And then this becomes 0.6786. Check that out. Add this number plus this number. If it equals this number, probably did something right. And remember, this 13% came from the 1 minus the 0.87. 1 minus 0.87 gives me 13%. So let's just see if we can continue on. It is believed that the vaccine will be effective in preventing 95% of them from contracting the disease a second time. So of those who contracted the disease, so we're looking at this column, of those who contracted the disease, it's believed it'll be effective in preventing the disease. Oh, so not the disease, which is going to be right here, 95% of the time. Well, that means 5% of the time it doesn't work. Okay? So when we multiply that out, we end up getting 0.209. And this becomes 0.011. I'm going to go ahead and add this all the way. Oh, and by the way, I should check this. This plus this should equal this. And in this case, I know that it does. Then I'm going to add horizontally. This plus this gives me 0.1124. This plus this gives me 0.8876. And when I check, this number plus this number should equal that. All right. Now, this is the so right here we have, these are the 22% that got the disease, 78% of the population did not get the disease. Of the 100% of the population who got vaccinated, once they're vaccinated, 88.76 won't get it. Of the population who's vaccinated, 11% will get the disease. This one right here, they already had the disease and they get it again, so they're getting it twice. Let's see if we can answer some questions. All right, so the first question, regardless as to whether or not an individual has previously contracted the disease, so regardless of whether or not they contracted the disease, what is the likelihood that an individual from New York City will not contract it after they've been vaccinated? So we don't care if they have the disease or not, but they've been vaccinated, and we want to know the likelihood that they won't contract it once they've been vaccinated. Well, so number one is just this value right here, that once you've been vaccinated, whether you've had it or not had it, the likelihood that you get it after you've been vaccinated is 0.8876. Number two, what proportion of the population never contracted the disease? That is to say, what proportion of the population did not contract the virus prior to the vaccine, nor did they contract it afterwards? Okay, so they're not going to contract it before, so they're in this column, and they're not going to contract it afterwards. So this is an intersection, and this intersection of not disease and not after vaccinated is 0.6786. And I'm going to go back and do that one more time, but with some colored marker. So here we go. It says the proportion of the population did not contract prior, so we're looking at this column. And then nor did they contract it after it was vaccinated. So I'm looking right here, and this is where it got circled twice. So that's my intersection. So that's my answer to that problem. So that's where I get the 0.6786. Number three, what proportion of the population contracted COVID-19 a second time? In other words, what percent contracted disease prior? So this is the prior column, so they already contracted it here. And then after they got vaccinated, they still got the disease. So this is my intersection, which is number 3. So number 3 is 0.011. That's rough people there. So 1.1% of the population in this scenario, 1.1% of the population of New York City will have the disease twice. What proportion of the population of New York City will have COVID either before or after the administration? As soon as I see the word or, I think union. All right. And as soon as I think union, I write down the general addition rule. General addition rule is a probability of A union B equals the probability of A plus the probability of B minus the probability of A and B. Okay, so in this case, what proportion of New York City will have had COVID either before or after? So I'm looking for the diseases. And we have this group got a disease, so I'm going to put that down as 0.22. And this group had the disease, which is 0.1124. Well, in that case, I still need to work with the intersection. Well, the intersection is where the two cross. And we see that it crosses at 0.011, so minus 0.011. When we run that through the calculator real quickly, 0.22 plus 0.1124 minus 0.011. And we end up getting 0.3214. So the answer to number 4 is 0.3214. Okay? All right. So, number 5. Given the probabilities, P equals 0.45 and the probability of PUN equals 0.63, what is the probability of N if P and N are mutually exclusive? So as soon as I say mutually exclusive, I go, oh, you know what? There's no overlap. So I know that there's no overlap. And as soon as I see this, I think general addition rule. So I'm going to go ahead and write the general addition rule down, and I'm going to write it in terms of this problem. So for number 5, we have the probability of P union N equals the probability of P plus the probability of N minus the probability of P and N. All right? So what do I have? Let's fill in what we have. We know that we have, this is 0.63, and we know that probability of P is 0.45. We don't know what N is, and we don't know what the intersection is, but wait, we do. It's mutually exclusive, so there's no intersection, so this is 0. All right? So in this case, I can just subtract, and I end up with 0.18 equals N. So the answer to number 5 is 0.18. The next one, given the probability P is 0.25 and the probability PUN is 0.64, what's the probability of N if they are independent? This is very key. And once again, I see the intersection symbol. All right, I see the union. As soon as I see that, I'm going to go ahead and write down the general addition rule, probability of P union N equals the probability of P plus the probability of N minus the probability of P and N. All right, so I'm going to start plugging in what I know. What I know is this is 0.64. And I know that this is 0.25. I don't know N, and I don't know my intersection, but they give me one other piece of information, and that is that they're independent. And if they're independent, I know that the probability of P and n equals the probability of p times the probability of n, because they're independent. We know this to be true. Well, I don't know everything, but I do know that this becomes 0.25 times that. So I can substitute this information right here. So this becomes minus 0.25n because it equals that intersection. So I just substituted it in. When I subtract 0.64 minus 0.25, I end up getting 0.39. And this is 1n minus 0.25n. So this becomes 0.75. Oh, excuse me, 0.75n. Checking my math out. Might have made an error. Wouldn't be the first time. All right, so I divide both sides by 0.75. And I end up getting n equals 0.52. All right, so this is the answer to number 6. N is 0.52. And once again, basically all I did was substitute my knowledge that because they're independent, P times N equals the intersection, and I plugged that in. Okay? All right, moving on to number 7. And to be honest with you, this problem ended up being easier than we intended, so fortunate for you guys. The number of points scored in a game has a probability distribution below. The number of points in one game is independent of the number of points scored in the second game. So we're playing 2 games. 2 games tells me I need to make a sample space or a table or something. When the game is played twice, the sum of the number of points for both games could be 0, 1, 2, 3, or 4. What's the probability the sum is 3? Well, since I'm playing the game twice, I'm going to go ahead and make a sample space of what can happen. I can either get a 0, a 1, or a 2, and I can get that on each game. So I can get a 0, 0, a 0, 1, a 0, 2, a 1, 0, a 1, 1, a 1, 2, a 2, 0, a 2, 1, or a 2, 2. All right? Well, they say they want the probability that the sum is 3. Well, here's how I get a 3. So that means I can get a 1, 2, or I can get a 2, 1. Well, the probability of a 1 is 0.3. The probability of the 2 is 0.3. The probability of this is 0.3, and the probability of this is 0.3. When I add those up, I end up getting 0.09. I ran out of room. 0.09 plus 0.09. And so the answer to number 7, and I'm going to write that here, 0.09 plus 0.09 equals 0.18. So the answer to number 7 is just plain old 0.18. All right, next one. An administrator at Reagan claims 17% of online students are failing 2 or more classes. What is the likelihood that in a random sample of 10 online students that at least one is failing 2 or more classes? All right, so we can probably do this binomial at this point, but at the time of the test, I don't think you knew how to do the binomial, so let's do this with what we knew at the time of the test. And then I'm going to relate it to the binomial. Claims that 17% of the students, online students, are failing. So the probability of failing is 0.17. The complement of that is 0.83 is my complement. What is the likelihood that in a random sample of 10 online students that at least one is failing? Whenever I see at least, I think, hey, I'm dealing with a 1- situation. All right. Now I have 10 online students, so I could have 0 fail, 1 fail, 2 fail, 3 fail, 4 fail, 5 fail, 6 fail, all the way up to ... 10 fail. What they want at least one means they're interested in this group. All right? So I can add the probability of 1 plus the probability of 2 plus the probability of 3, and add all those probabilities up and the probability of 0. If I add up all those probabilities, it sums up to one whole. If I add up all those probabilities. But that's a lot of work figuring out the probability of all of these and adding them up. It's just easier to subtract out the probability of 0. So we're going to do 1 minus the probability of 0. Well, that means we're not, and that's probability of their not failing. So 1 minus the probability of not failing, which means if they're not failing, that means 1 probability of all passing. All right, well, we have 10 people and they all need to pass. What's the probability of passing? 0.83 times 0.83 times 0.83, so 1 minus 0.83 to the 10th power. So that would be how we would do this based on what we previously knew. 1 minus 0.83 caret to the 10th power, and we end up getting 0.8448. So this is my answer. All right, and remember, whenever it's an at least problem and you work it this way, you're working with the complement. And sure enough, the complement of the 17 was this, and we just and that gives us the probability of 0. Now that I'm going to relate that to what we've recently learned this week, which is the binomial. And if I were showing work on the binomial, I'd have to do this. I'd have to go 10, choose 1, and the probability of one failing is 0.17 to the first times the passers. 10 minus 1 is 9 plus dot 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 plus, and 10 choose 10, 0.17 to the 10th power times 0.83. 10 minus 10 is 0. So that's our work shown. That's what we would do for our work, and then we plug it in the calculator. But what are we plugging into the calculator, and how does that relate? When the calculator, we're still going to do a 1 minus because it's an at least problem. We know it's a binom, and we know it's a CDF because we have multiple values. Well, whenever it's the 1 minus, we subtract out what we don't want. But first off, our number of trials is 10. Our probability that they fail is 0.17. And our x value is the one that we subtracted, which happens to be a 0. So on the calculator, this would look like this. 1 minus second vars, binomial, CDF, trials is 10, probability that they failed is 0.17, and we wanted to subtract out using the x. And there we go, 0.8448, which is exactly what we got here. But you're like, I'm not exactly sure I follow how this relates to that. Okay, so what does this look like? Well, this looks like 10, choose 0, 0.17 to the 0, 0.83, 10 minus 0 is 10. Well, guess what? This is 1 and this is 1, and we're left with this. And since it was an at least, we have the 1 minus. So 1 minus 0.83 to the 10th, which is what we showed right there. Okay? All right. Maybe a little more information that you wanted, but I do want to relate those two problems to the binomial. And now that you know how to use the binomial, you can use that on the test. All right. 30% of candies in a bag are brown, 20% are red, 15% are yellow, 10% are green, and the rest are blue. If 5 candies are drawn with replacement, what's the probability none are blue? Okay, so first off, I had this problem, and when I went to design this problem and make sure I had it right, I went 0.30 plus 0.2 plus 0.15 plus 0.1 plus b. And I know that they all needed to sum up to 1 in order to be a valid probability distribution. So 0.3 plus 0.2 plus 0.15 plus 0.1 equals that. So I know that B, they added up to 0.75. So B equals 1 minus 0.75. So B equals 0.25. Well, they say they want none or blue, and I'm drawing 5 candies. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Not blue, not blue, not blue, not blue, not blue. So this is going to be, the probability of blue is 0.25, so not blue is going to be 1 minus that, which is 0.75. And I'm pretty smart at the very end and go, you know what? I just go 0.75 to the 5th power. So let's try that out. 0.75 to the 5th power. 0.2373. All right. So the answer to number 9 is 0.2373. All right. So number 9 is 0.2373. Number 10. A complex electronic device contains 3 components, A, B, and C. The probabilities of failure for each component in any one year are 0.02, 0.04, and 0.08. If any one component fails, the device fails. So that's, when I say if any one, that means at least. And so as soon as I say at least, I start to think that I might be working with a complement. I may not be, but I start to think that I'm working with a complement if I see something that means at least. And I'll always think about a 1 minus situation, and I always think about a complement when I say anything that relates to at least. So if the component fails independently, this is important because they're independent, that means I can multiply them of one another. What's the probability that the device fails in 1 year? All right, so here we are. We think we're working with a complement. All right, so if this one fails, or if this one fails, or if this one fails, or these two, or these two, or these two, or all 3 fails, the device fails. So I can figure all those individual all those probabilities out, or I can go, you know what, this isn't an at least problem. So I can do 1 minus the probability that the device does not fail. So we're going to be working with a complement in this situation. So the complement of 0.02 is 0.98. The complement of 0.04 is 0.96. The complement of 0.08 is 0.92. Now let's talk for just a moment why I'm doing this. Like, I'm doing this because I want extra credit. Okay, besides the extra credit, why am I using the complements? Because this right here tells me it's not failing, not failing, not failing. So the probability, so if I multiply this together, this right here, this part that's in the brackets, is the probability the device does not fail. Well, if I have the probability the device does not fail, and I subtract it from 1, then I have the probability that it does fail. Okay? Because this means all 3, because if we have 3 devices, 0, 1, 2, 3. If any of these fail, the device fails. So 1 minus the probability that none fail is the probability, 1 minus the probability of none fail leaves me this, which is the probability of failure, because this is the probability of none fail. So I don't know that I did the best job explaining that, but I tried. So 0.98 times 0.96 times 0.92. 1 minus that gives me 0.1344 or 131. So 0.1344. Of course, if you round it up to 0.1345, that was perfectly acceptable. All right, so that's my answer to number 10. Okay, number 11. A weighted 6-sided number cube is numbered with numbers 1 through 6, with a different number appearing on each face. On the number cube, the probability of 1 is 0.2, the probability of 2 is 0.5, probability of 3 is etc. What is the probability that the first 6 is the fourth number rolled. So let's look at this. So we can get a 0.2. That's a 1, 2, 3, 4, 5, and 6. The probability of a 2, 0.15. The probability of a 3, 0.10. The probability of a 4, 0.15. The probability of a 5 is 0.2. So I don't know this, but I know if I add all these up, it has to be a valid probability distribution, and that has to equal 1. So let's do that real quickly. And 0.2 plus 0.15 plus 0.1 plus 0.15 plus 0.2. So 1 minus 0.8 gives me an answer of 0.2. All right, so this is 0.2. So the probability of a 6 equals 0.2. What is the probability the first 6 is the fourth number rolled? Probability the first 6 is the fourth number rolled. So 1, 2, 3, 4. So this is a 6. We want the probability of a 6, not a 6, not a 6, not a 6. The probability of a 6 is 0.2, and not a 6 is going to be 0.8, because that's just a complement, 1 minus the 0.2. Rolling the dice is independent. So here we have 0.8 to the third power times 0.2. Oops. So I end up getting 0.1024. All right, and that's the answer to number 11, 0.1024. Number 12. Approximately 12% of hobbits born in the Shire are from multiple births. That's twins, triplets, etc. Of the hobbits born in the Shire who are from multiple births, 70% have hairy feet. Of the hobbits born in the Shire who are single births, 10% do not. The table organizes the information above. Really, they didn't have to give you the whole table, that information, but they did, and that just tells you where these numbers came from. So the question, if a hobbit is selected at random, what's the probability he has hairy feet or was from a multiple births? This right here, that tells me I'm looking at a union. Be really careful. So what we care about in this problem, probability has hairy feet or was from multiple births. So probability, I see the or, so I'm like, this is a general addition rule. So probability A union B equals the probability of A plus the probability of B minus the probability of A and B. Okay, so A is 0.12. That's multiple births. Hairy feet, 0.876 minus the intersection or minus the overlap. And when we do that, 0.12 plus 0.876 minus 0.084, we end up getting that number 12 equals 0.912. All right, so that's number 12. All right, number 13 is working with the same table, so I'm not going to read it again. But we have a given. And anytime I see a given, I always go, okay, I'm going to write given. And I know that I should be thinking about having an intersection on top. So given that a hobbit does not have hairy feet, all right, so that means I'm looking at this, in this case, this row. And you know what? Not have hairy feet is 0.124. What is the probability that they are not from multiple births? So I'm now looking at this, and there's my intersection, 0.088. .088 divided by 0.124 equals 0.7096. 0.7096. And if you round it up to 0.7097, of course, that was completely acceptable. That was full credit response. All right, number 14. Goblins and their offspring slobber to attract mates. There's a 72% chance that both of a goblet's parents have the slobbering gene. It is known that the distribution of the slobbering gene is independent of gender. When he meets with goblet parents, Mr. Spencer likes to meet with them one at a time. Due to the goblin family hierarchy, Mr. Spencer always meets with the female parent first. The probability that the female goblin parent carries the slobbering gene and the male goblin parent does not carry the gene is 8%. What proportion of female goblin parents have the slobbering gene? Okay, first off, that's just a confusing problem. It is. Once again, when I have confusing problems, I look for a way to start to organize it. And I go, well, what do I have? I have a 72%. Well, I don't see my three numbers, so I'm not sure that a table applies. But it does say both. So that means I'm working with two variables possibly. And so we know that we have, we see the word independent, that's important. We have a female parent that has a slobbering gene, and we have a male parent that has a slobbering gene. It's like, you know what? I have two variables. Let's see what we can do with the two variables, and let's see how far we can get. And I'm going to call this FSG, female slobbering gene, FSNG, female, or FNG, female not slobbering gene. Male with the slobbering gene, male no gene. All right. So what do I know? Well, I know this number. That's about all I know right now. There's a 72% chance that both, well, both goes here, always. And it's not conditioned. It doesn't say of this, it just says there's a 72% chance that both. So that means there's no multiplication. They just define it specifically as both. It is known that the distribution of gender and the probability that the female goblin parent carries the slobbering gene and the male parent does not carry the gene is 8%. Female carries the gene, male does not, that's 8%. Add those together. 80% chance that the female carries the slobbering gene, and that was the actual answer to this problem. And that was the answer that was accepted. There was actually a typo on this. This is what you all received. This was the answer that was correct for what you all received. This was not supposed to say female. That was supposed to say male. Had it been male, this problem becomes a little more difficult because I don't have any more information, and I need this value right here. But they tell me that this was supposed to be independent. And I know this, the probability of A and B equals the probability of A times the probability of B if they're independent. So my intersection was 0.72 equals 0.8 times B. So when I divide that out, I end up getting 0.9 equals B. So what I had meant to ask, not what I asked, so this was not the answer, this was the answer on the test. What I meant to say is what's the probability that the male carried the slobbering gene? And there's a 90% chance that the male carried the slobbering gene because 90 times 0.8 gives me the 0.72. All right, so that's number 14. And then we're off to number 15. Once again, this is very similar to the problem that they had on the first test. The numbers were changed. And also these numbers are fake. These do not apply to the Kodiak bears. But Kodiak bears, typically have two baby cubs, two bears called cubs. When there are two cubs, the mother bear always feeds the older bear until it's at its foot fill, and then she feeds the younger cub. The results is an unequal chance of survival for the two cubs. Suppose that the older cub has a 95% chance of survival. If the older one survives, the younger cub has a 60% chance of survival. If the older cub does not survive, the younger cub has an 80% chance of survival. What's the probability that at least one cub survives? So we're looking at least one cub. Well, here, the older lives, the younger lives. That means two cubs live. The older lives, the younger dies. Well, the older lives, the younger dies. That's only one. Here, the younger lives, the older dies. That's one. Older dies and younger dies. No cub survive. So in this case, 0.83 or 0.38 plus 0.04 equals 0.42. So the probability that at least one cub survives is 0.42. Please make sure you write your answers neatly in a well-ordered manner so that you can receive the credit for having done this.